All right, let's talk about something that sounds, well, completely backwards. What if I told you that sometimes, to solve a really hard problem, the best answer is one that's technically wrong?
I know, it sounds crazy. Why on earth would a computer scientist, someone who deals in pure logic, celebrate a solution that isn't perfect? But believe it or not, this very question is at the heart of how we solve some of our biggest, gnarliest problems, from designing the chips in your phone to building out the internet itself.
You see, here's the deal. There's this whole category of problems called NP-hard, which is basically just code for impossibly difficult. We're talking about puzzles so complex that finding the one single perfect answer would take the fastest supercomputer we have longer than the age of the universe. No joke. So what do? You get clever. You find a workaround. And that's where these approximation algorithms come in.
The idea is pretty brilliant, really. Instead of spending billions of years looking for that one perfect needle in an infinite haystack, we find a really good needle super fast. And the best part? We have a mathematical guarantee that tells us exactly how good it is. These algorithms are the unsung heroes for tackling problems that seem completely impossible. To really get a feel for this, let's look at a classic example. It's a fundamental puzzle that pops up all over the place, from designing computer chips to building massive communication networks. And that puzzle is called the Steiner forest problem. Just picture this. You've got a bunch of locations, say data centers or even houses in a new neighborhood. You need to connect specific pairs of them with fiber optic cable. The goal is simple. Do it using the least amount of cable possible to save money. That right there is a Steiner forest problem.
Now, people have been wrestling with this for years, and they've come up with all sorts of different algorithms to try and crack it. So what we're going to do is look at this really cool study that basically threw 4 of the main contenders into an arena to see which one came out on top.
Okay, in the first corner, we have PDSF, the primal dual. You can think of this one as the seasoned champion. It's the one everyone recommends. It's fast, it's reliable, and it has a solid mathematical guarantee behind it.
Next up, meet PGSF, the paired greedy. This one's the scrappy underdog. It's called greedy because it does the simplest, most obvious thing at every step. It just finds the 2 closest points that need connecting and connects them. That's it. It's so straightforward you'd think there's no way it could compete. And right alongside it is another greedy algorithm, GLSF, the gluttonous. Kind of similar, but its strategy is to group nearby points together first before it starts making connections. And finally, we have TMSF, the tree metric algorithm. This is the total opposite of the simple guys. It's the complex, theoretical heavyweight in the ring, using all these fancy, advanced, randomized methods. It's got the brains, but does it have the brawn?
Okay, so we've got our 4 contenders. The big question is, how do they actually do when the rubber meets the road? Theory is one thing, but performance is another. Researchers put them through the ringer. They tested them on a huge library of about 1,200 different network problems. And the results? Well, they were pretty surprising. What you're seeing here are 2 charts. On the left, we've got speed, how long each algorithm took. Lower is better. And on the right, we have the quality of the solution, so how cheap the final network was. Again, lower is better.
And just as this quote from the study says, the old champion, PDSF, that's the yellow bar, was an absolute speed demon. It blew the others out of the water, consistently faster, sometimes by a huge margin.
But here's where it gets really interesting. The big surprise. Remember that super simple, scrappy underdog PGSF? It produced solutions that were just as good, just as cheap as the champion. The simple, greedy approach totally held its own.
And this table just drives that point home. It's this perfect illustration of the gap between theory and practice. Look at PDSF. On paper, its worst-case guarantee says its solution could be twice as expensive as the perfect one. But in reality, it's almost perfect. And then look at PGSF, the simple one. It has no fancy guarantee on paper, none. But in practice, it's just as good. Meanwhile, the super complex TMSF, in the real world, its solutions were way, way more expensive.
Okay, so this whole idea of a theoretical guarantee brings us to an even bigger story. A story about a single number that represented a massive 35-year-old barrier in computer science. And that number is 2. For decades, the absolute best anyone could prove for the Steiner forest problem was what's called a 2 approximation. All that means is that the algorithm was guaranteed to find a solution that was no more than twice the cost of the absolute perfect one. And for the longest time, nobody could do better. I mean, this barrier was established way back in 1989. It stood for over 35 years.
The paper that said it even won a Test of Time award. Most people in the field thought it was a fundamental limit that you just couldn't beat it. But then, very, very recently, something happened.
A new paper came out. A team of researchers announced they had done it. They had done it. They had created a new algorithm that finally and definitively broke that barrier.
And what was the new number? It was 2 minus 10 to the power of negative 11. Now, that looks like a ridiculously tiny improvement, right? Just a tiny little sliver better than 2. But in the world of theoretical computer science, that tiny sliver is a monumental leap. It's like breaking the sound barrier. They solved one of the biggest open problems in the entire field.
So, okay, let's bring this all together. We've talked about practical showdowns and 35-year-old theoretical barriers being smashed. What's the real-world takeaway here?
Well, a few things. First, theory is a fantastic guide, but you've always got to test things in practice. Second, for day-to-day problems, a fast, reliable workhorse like PDSF is probably your best bet. And third, never underestimate the power of a simple, greedy idea. But maybe the biggest lesson is that it's that relentless push to break theoretical boundaries, even by a tiny fraction, that opens up entirely new ways of thinking and moves the whole field forward.
It's a great reminder that there's always another frontier to explore, which kind of leaves you with one last big question to chew on, doesn't it? What other impossible problems are out there, just waiting for one tiny breakthrough to crack them wide open?